So how do you do it? How do you build something just insanely complex, like a rocket to the moon? I mean, think about it. You've got a million parts. Every decision is life or death, and you're probably using technology that you have to invent along the way. It sounds impossible, right? Well, it turns out there's a specific way of thinking, a structured approach designed for exactly this kind of challenge. And here's the secret. When you're staring down the impossible, you don't start by, grabbing a wrench. You don't start building. You start by asking questions. And not just any questions, the right questions. This is the whole philosophy, really, behind a discipline that's all about turning absolute chaos into crystal clarity. And that's what this is all about. We're going to unpack that discipline, diving into both the art and the science of making the impossible possible. Think of this as your primer on systems engineering. All right, so here's our game plan. We'll start with what systems engineering actually is. Then we'll talk about why the first step is everything. After that, we'll look at how you pick a path when you've got options. And we'll wrap up by looking at why the best solution is rarely the perfect one. Okay, first things first. What is systems engineering? Well, at its core, it's really the discipline of seeing the whole picture. It's about getting out of the weeds, Instead of staring at a single tree, you're climbing a mountain to see the entire forest. It's all about understanding how every little piece fits and works together in the grand scheme of things. Now, if you look up the textbook definition, you'll see words like interdisciplinary approach. And yeah, that's true. But the really crucial part, the thing you need to remember, is this. It's all about nailing down what the customer actually needs right at the very beginning. We're talking super early in the process. It's about obsessing over the what. What does this thing need to do long before you ever get bogged down in the how? Why? Because it stops you from building a beautiful, flawless, perfectly engineered solution to the wrong problem. And this table here? It's a perfect way to think about it. Let's say you're building a dog kennel. You can pretty much just go for it, right? One person, a few simple tools, no biggie. But now let's scale up. You're building a house. Okay, now you need a team. You definitely need blueprints, power tools, a real process. But a skyscraper? Whoa, now we're talking multiple companies, incredibly rigorous analysis, huge industrial machines, and a master plan that's just mind-bogglingly complex. Systems engineering is the thinking you need as you make that leap, as you scale from that simple kennel all the way up to the skyscraper. And that thinking doesn't just stop once the thing is built. Oh no, this discipline covers the entire life of the system. I'm talking from the very first spark of an idea, that's the concept stage, all the way through building it, using it, supporting it, and even, eventually, retiring it. It is quite literally a cradle-to-grave way of looking at things. Which brings us to what is, without a doubt, the most critical part of the whole process. Section 2, we're calling it the art of the start. Because here's the thing about systems engineering. The decisions you make before you've even sketched out a single component, those are the ones that will make or break your entire project. So this all-important concept stage isn't just guesswork. It follows a really clear, structured path. Step 1, situation analysis. This is where you dig deep to make sure you're even solving the real problem. Step 2, synthesis. You come up with a bunch of different potential solutions, and I mean really different, not just tiny tweaks. Then you evaluate them. You look at the trade-offs. And only then, after all that work, do you finally make a decision and pick the best way to move forward. And what's so fascinating here is the philosophy behind that very first step. Most projects jump right in with the question, okay, what should we build? But a systems engineer, they pump the brakes. They take a step back and ask a totally different question. Hold on, are we sure we understand the root cause of the problem here? Or are we just slapping a Band-Aid on a symptom? Getting that distinction right at the beginning, well, it saves you an unbelievable amount of time, money, and heartache later on. So that brings us to a huge piece of this early puzzle, choosing the overall architecture, the big picture approach. And honestly, there is no better, more high-stakes example of this in history than how NASA figured out how to get to the moon. I mean, just try to put yourself in their shoes for a second. How on earth do you choose a master plan for landing on the moon when most of the tech you're going to need doesn't even exist yet? It's an insane challenge. And this is exactly why that process of coming up with and seriously evaluating totally different ideas is so absolutely critical. Okay, so option 1 on the table was called direct ascent. The concept was simple. You build one single absolutely massive rocket. We're talking bigger than anything ever imagined. It flies straight to the moon, the entire beast lands, and then that same entire beast takes off and flies home. The plan itself? Super simple. The catch? The rocket would be a monstrous, totally unproven leap into the unknown. All right, option 2, Earth orbit rendezvous. The thinking here was, hey, let's use rockets we're already comfortable with, launch the mission in a few different pieces, and then assemble the final moon vehicle up in Earth's orbit. So the hardware was way more familiar, which was a big plus. But the process? You're basically talking about building a spaceship in space. A completely new, totally terrifying challenge. And then there was the third idea, the dark horse, the one that ultimately won, lunar orbit rendezvous. Here, the main mothership stays safely in orbit around the moon, and it sends down this tiny, specialized lander, like a little space spider, to the surface and back. Now, the genius of this is that it's insanely efficient. You're not lugging all that fuel for the trip home down to the moon and back up again. The downside? It all hinges on this incredibly risky, nail-biting docking maneuver, 250,000 miles away from any help. So, with 3 very different, very risky options, how in the world did they decide? Well, it wasn't a gut feeling. They used a structured tool, something just like this, a value-benefit matrix. It looks complicated, but the idea is simple. First, you list your main objectives, what matters most. Then you give each one a weight based on how important it is. Production cost, for instance, got a huge weight of 50. Then, you score each option against each objective. So variant C here got an 8 out of 10 for production cost. You just multiply the score by the weight. 8 times 50 is 400. You do that for every single box, add them all up, and you get a total score. Just like that, you've taken this massive, complicated, emotional decision and turned it into a clear, data-driven choice. And look at that. Variant C, lunar orbit rendezvous, wasn't just the winner, it was the runaway winner. But, okay, even after you've picked your big picture architecture, you are far from done. And this brings us to our final section and a really deep philosophical point, the perfect compromise. Because this gets to a fundamental truth of engineering, and maybe even life. The best solution is almost never actually perfect. It's a bundle of trade-offs. Let's bring this down to earth with a simple example, a washing machine. The person designing it has to make a ton of choices, right? How powerful is the motor? How much water does it use? How much electricity? What kind of metal or plastic do we use? How much can it cost? And here's the key. Every single one of those choices bumps up against every other choice. A stronger motor? Great, it cleans better, but it also costs more and uses more electricity. This tangled web of interconnected decisions, that's what engineers call the trade space. So how do you navigate that trade space without going crazy? Well, engineers have a really powerful tool for this called the Pareto front. The easiest way to think of it is as the line of best compromises. It's basically the collection of all the best possible designs. Any design on this line is optimal, which has a very specific meaning. You literally cannot make it better in one way, say performance, without making it worse in another way, say cost. Let me show you what I mean. Okay, let's look at this visually. Imagine we're trying to design that washing machine, and we want to make it as cheap as possible and also use as little energy as possible. So we map out every single possible design combination as a dot on this chart. And what's the first thing you notice? There's no single dot down here in the perfect corner, the one that's both super cheap and super efficient. The perfect design, it just doesn't exist. So the first thing we can do is start getting rid of the obviously bad ideas. Take a look at this one dot here. This is what's called a dominated solution. Why? Because you can easily find other options up here that are both cheaper and more efficient. It's a total lose-lose. So we can just wipe all of those bad options right off the board. Now, after you get rid of all those lose-lose designs, what you're left with is this beautiful, elegant curve. This is the Pareto front. Every single point on this line represents a winning design, an optimal compromise. And here's the genius of it. The hard engineering work is basically done. The choice now isn't about engineering, it's about priorities. Do you, the customer, want the one that's a little cheaper or the one that's a little more efficient? There's no wrong answer on this line. They're all the best. They're just different. And that right there is really the heart of it all. Systems engineering isn't some magic wand for finding one single perfect solution. It's not about magic bullets. It's a structured philosophy. It's a way of thinking that gives you the tools to wrestle with insane complexity and, in the end, make the absolute smartest choice you can from a whole universe of imperfect, real-world options. And you know, this kind of thinking, it's not just for rockets and skyscrapers. Think about the big, complex decisions in your own life. Planning a career, figuring out your finances, even organizing a project in your community. These are all complex systems, and they are all full of trade-offs. So I'll leave you with this question.
How can you take a piece of this structured thinking to help solve the impossible